Hello, this video is about the lattice structures modeling, and I'm going to show how to do that for a Kagome Unit Cell lattice that is 3D printed. In this video, we're going to start with unit cell, and then we'll move on to how to model a compressive behavior as well as a shear response for this material. So let's sit back and relax as we get started with this modeling. Welcome to CM Videos. My name is Dr. Michael Okereke. The reference publication we're going to use for this modeling is this publication, and if you look more closely, basically you would see it's a mechanical response of a titanium 3D Kagome lattice structures manufactured by a 3D printing method called the selective laser melting. So we're going to build this kind of model, and we're going to do a compressive response of this model as well as a shear response of that. So this is a format of the 3D printed structure. So in terms of our unit cell, this is the sort of unit cell that we hope to create here. And looking more closely on this unit cell, so the Kagome structure is basically what you see right in the middle here, and the upper and bottom base plates are made of the same material because this is completely 3D printed from the beginning to end. The domain, the virtual domain for this would look like this. So basically you've got a length, you've got a width, you've got a height, as well as a thickness associated with the system. And then the strut dimensions, which basically looks like this, it's oriented at 45 degrees, and the diameter of the strut is 0.75 millimeters, and the angle of inclination is 45 degrees. There's the length, and the design is obviously a Kagome lattice structure. So the material that we're going to use to do this model will be a titanium alloy material with the properties given in this case. So this titanium alloy will be 3D printed, and so the properties of the 3D printed titanium alloy is what we have here, and these are the details of the publication where this information is taken from. The case studies that we're going to be looking at will be one, a uniaxial compression in the y-axis, as well as an in-plane YZ shear deformation. If this is the kind of content that you like, please do consider subscribing to this channel and click the like button or share the content so that other viewers can benefit from the content that is created here. So we're going to go into Abaqus and begin this modeling. Here we are in Abaqus. So the first thing we need to do is to create the parts. So it's going to be created by sweeping method. We need to create the length, could be minus 7 up to 7 that bit. So now we need to sketch our circle. So 0, 0 is the origin, and 0.35 and 0 is the size, 7 millimeter diameter. So that's the first strut. So we'll copy this strut, create the second strut, but we need to rotate this by 45 degrees. So we change the part name, and to make this possible, so we need to create a center line. Okay. Now, so we press and hold, select this rotation, move this. So select that, select this. So it gives us that direction, so this is fine. Now we just go back to the top and regenerate. So we now have the two structures in place. So we'll go to the assembly module and bring in the two instances. So they're fine. So we now merge them. So we'll create a second instance of that strut. Okay, so the two of them exist now. So what we need to do is to rotate this further. So basically we are selecting the second strut, and we rotate it about the y-axis and 90 degrees. So we now have sort of the elements of the unit cell. So the next thing we need to do here is, if you check in this, so if you notice here that these struts are actually oriented along the 45-degree direction. They're oriented along the 45-degree direction. So the inclination is diagonal. So we're going to have to rotate this by 45 degrees. So I'm going to select basically this button to rotate. So we select everything. So how do we want to rotate it? About the y-axis, and 45 degrees is the orientation. So this looks like right. So it looks okay. So we then need to match cut. So I'm going to call this my strut unit cell. Okay. So we select everything. So we've got the strut unit cell in the way it should be. So we now need to create the plate. So the base, the plates. So what form we're going to use? Extrusion. So right at this corner, so this will be minus 6.30 and 6.3. Okay, so this is the structure, and the extrusion depth is 12.6. So we've got that. So we then bring it into the model here. Now what we need to do is to do a linear patterning of that, so that we can get it looking right. So we take this off we change the direction of orientation of that, okay, and then this becomes 6.3. Then we need to delete this bit because we just use it as a reference. So what we then need to do next is do a linear pattern of that. So we select that. So what we need to do with this in terms of how high we want it, okay, we don't want it that, so we want it in the y-axis, and then we flip it around, so it's right there. So what we need is basically have the length of the strut times the sine 45 degrees of it plus the length of the base. So we put it in here, so put this value in there, so this is okay. So we do the same linear pattern of this middle one, okay. So we now start again, we don't want this axis, so we want it oriented in the y-axis, and we flip it around. But the height we just need is this 45 because the base is no more included in the calculation, the base height. So we've got that. Everything looks symmetric and it's fine. Okay, so just before we leave, so we're going to probably delete the middle one because that was just there for a reference. So we delete that, and then we now merge everything. So I'm going to call it KLS units. So everything is included in this model here. So we're going to then extrude cut. So select there. So what we're going to do is that we need to introduce some construction lines, one here and then another construction line at that boundary. And then we could then go and, okay, so we start from there to this point. This is fine. So the structure works out correctly like that. So then we'll do the same on the side here. So we start again using a construction line right there and then right here. So that looks all right. So we could then specify, so from that corner to here. Okay, so this is fine, and then we can build. So now we have the right unit cell structure with the diagonals now, with the strut oriented diagonally like we expected it to be. So what we then need to do next is just to create the duplicates of that. We will then need to go back into the assembly module, create the duplicate by creating a linear pattern, select the instance to pattern. So clearly we don't want some axis, so we basically need to probably remove the base one. So we've got this axis looking right. And then the next thing we need to do is to also create a linear pattern, select the two together. Now we don't want this axis, so we probably want it to move in the Z direction. Okay, so we now click done. However, we need to translate. So we'll translate the two from this corner, from the bottom corner here, so that it makes connection with this other end. So basically we've got the structure. So the final thing we need to then do is to create a merge. So we'll call it all KLS. So we want to remove all the intersecting boundaries, everything. So we'll put them all together, and then we'll have a clean structure to mesh. So we'll select all that, okay? And then select what type of mesh we want. So tetrahedron normally is fine. And then we can mesh the structure. So the structure is meshed and ready to simulate. So still within the ALS unit cell structure. So can we create some set Y top? So let's call that Y top. So we just select the top, and then we'll also do the same with the Y base. So that will be the base of the structure. Now the next thing we need to do is to create a reference point, which we are going to use at this point. So we'll create a reference point set. So that will be associated with this point. The step, so we can work with a static loading step. Our history output will be history output. So this will be associated with the reference point. And we are looking at RF2 and U2, RF3 and U3. So we need to create a constraint equation. So constraint will be associated with this. So basically, we are associating 1 to the top in the two direction with the reference point and -1. So this is basically linking the behavior here to that point. So what will our boundary condition? So I'm going to say fixed Y base. So it will be a displacement boundary condition. So we select the Y base. So we'll fix it in every possible direction because we're looking at doing compression. So this is fine. And then our loading will be Y compression load. So it's associated with a static reference frame, and we are looking into the reference point. And the direction that we want to, we can fix everything, but the only part we are really keen on is the y-axis. So a reference point, so -3. Then we need to think about the material models that we want. So what will be our material? So we're looking at titanium alloy. So a titanium alloy model would have an elasticity. So our plasticity. So we also want to add some ductile damage failures. So we could do 0.10, 10% strain, triaxiality in compression is 0.33, and the strain rate will be 0.01. So just a static strain rate. So we've got all that structure. So what about our sections? A 3D printed material. Okay, so we can then go back to ALS and do this section assignment. So we select everything here, and then it's a titanium alloy structure. So we've got that, and it's meshed. The whole model is set up. So we changed. So I renamed the model here. I'm going to call it KLS Y comp, and then we can create the job Y comp, and then we can create a copy of that. So we'll create a copy, and then I'm going to call it KLS YZ Shear. So with the shear, everything remains the same. The only part we need to change is the Y comp load. So the Y comp load will no more be on that axis. So it will now switch to the Z axis because we are doing YZ, so it's in the Z direction. So it's moving that way. And our constraint equation will change. So our constraint equation would now be in the Z axis, but every other thing will be the same. One more boundary condition is the Y top roller. So we need to put a roller support at the top. What would that mean? So we select the top, Y top, and then we are allowing it freedom. So it's constrained in other direction, but it's free to move in the third axis, so that it basically allows movement in the third axis. So we'll have a YZ deformation. So everything looks the same, so we can then create job KLS YZ Shear. So we've got those two models, so we then submit it, and then we'll look at the result. Okay, so here are the results from the simulation. So what we're looking at here is the compressive behavior in the y-axis with damage incorporated, and then you could see the behavior, the simulation. So each of these fibers are obviously undergoing some kind of finite deformation. So if you keep increasing the deformation history, then this structure will probably ultimately start failing by buckling. So if we change it to plasticity, so you can see what's happening, that there are plastic regions around the structure, but there's not a lot of it. So the loading that we've included here is not significant to cause buckling of the structure. So you probably need to go beyond the 30% strain that we've imposed on this model. You need to go a little bit higher than that, so you can begin to see damage in the structure. It does show us the kind of nice behavior with the top moving and the bottom not moving as much as you would expect here. So that's the behavior of the structure while compressive deformation. So the next thing we need to do is to look at the shear case. So if we switch to the shear case, so now you can see at the 30% shear strain that we've imposed on this model, it's shearing a lot, and right at the connectivity there, you get a lot of shear deformation building up in the structure. So if we switch to plastic strain, it tells you, okay, the structure has actually exceeded the strain that we specified. So there's quite a lot of strain, nearly 10% plastic strain. So this is why we're getting a localized failure in shear. So we can look at formation. So clearly the top end is moving significantly due to the shear load, but the bottom is not moving a lot. And that's what you see in this simulation. So the final thing we can do, if we go back to the Y compression, is look at the data. So if we'll look, okay, fine. So we clearly are interested in the Y-axis behavior. So you plot that data, and then it shows you what's really happening. So there's a kind of elastoplastic behavior on the structure. So once plasticity is reached, you get this plastic deformation in the structure. So if we move this around to the shear strain data, so we could see what's happening with the shear strain. Again, you go, and the shear strain will be the y-axis, the third axis result. So again, you get some interesting results of the profile elastoplastic behavior. If you're interested in learning a little bit more about lattice composites, both in terms of how you can use periodic boundary condition to do it, there's a video that I put here. And then this is just, again, another video on lattice composites for you to check out for in terms of a body-centered lattice structure. Thank you for your interest in this video, and catch you in the next one. Bye-bye.